going to discuss about PD flow physical design. So this is the content we had. So the outline of the PD flow was physical design introduction and inputs of physical design flow, import design, partition and floor planning, power planning, placement, CTS and routing, physical verification, DFM checks, LEC, parasitic extraction, timing HTA and tape out. So these are the steps that need to be performed during physical design to develop a chip. So this is the ASIC design flow. Coming to the ASIC design flow, initially we'll be having the system specifications and the architecture design. So system specifications is given by the customer. According to that, the architecture is going to design, and the RTL is nothing but the Verilog file that is written Verilog language, and verification is what we do. We write a test bench, and we test whether our .v file is good or not. And synthesis is nothing but converting the .v architecture from format to RTL to gate level netlist. So in this in the design we are doing, in the physical design we are doing creating floor planning, placement, routing and CTS, and the mask preparation, fabrication and packaging and testing. So mask preparation is nothing but the fabrication, like preparation is at the sign off, what we say is, and ship, and we combine all the blocks and all the ICs and create a chip. So physical design introduction. So in the physical design introduction we used to say it as the initial stage as PNR and the sign off, and the bottom stage we used to say is sign off. In sign off we used to get a parasitic extraction, physical verification, formal verification, HTA, power, IR drop, tape out, like all these things what we used to say is, this is nothing but verifying whether there is no any like bugs in my design, like DRCs are nothing but there are some specified rules that we need to follow during development of my chip. That is what we need to do, right? Coming to parasitic extraction is nothing but whenever we are getting all the after route, right, we used to get the complete chip. So we need to verify whether this chip is going to tape out or not. Like we used to give RLC format. I can show it in the next slides. And so coming to the PNR inputs, so physical design inputs, .v file. .v file consists of standard cell instances and macros and memories instances. So instances is nothing but everything that has a specified name. So instance can't be same name. So if a macro having a specified name, it is an instance. So if a standard cell having a specified instance name, it is an instance. So macro pin, everything comes under the instance. So netlist also consists of standard cells and macros and interconnections between them. So nothing but interconnections are nothing but the wire connections. So constraints, coming to constraints, design rule constraints, optimization constraints. Design rule constraints are nothing but DRVs, max transients, capacitance, fan out and clock uncertainties. So coming to constraints, right, I will explain here. So this is a buffer, let us consider. So whenever how much input transient I am giving, how much output transients I am getting, so 50%, like 50% of it we say it as from 20 to 80% we say it as rise time, and 80 to 20% we say it as fall time in the slew period. So that is what we need to mention, the how much the input transient, and fan out, how much this buffer can handle, how many fan outs, how many fan outs, like how many, these are the fan outs we used to say. So and next coming to capacitance. So output capacitance. So output capacitance is nothing but the gate capacitance and the internal capacitance of the buffer plus the output load capacitance is we used to say. So that is capacitance. And so clock constraints are nothing but skew plus jitter plus margin. So setup margin, or it may be hold margin, we will discuss it later. So coming to the constraints from the designer, like there are two types, right? Design constraints and the optimization constraint. Timing constraints, coming to the timing constraints like exception paths like false path and some multi-cycle path, that we need to specify. The tool cannot know, right? So we need to specify this is a multi-cycle path. So my tool don't optimize that path. If it is a false path, right, unnecessary, there will be a optimization happening in that place. So I don't wanted to do the unnecessary things. So design delay constraints, latency, input delay, input transients, those things we need to mention in .sdc file. And power and area constraints and system interface is nothing but the interface, like which while load model or those things. If it is, that is not an other, there will be another file. Actually there is a qrc tech file, in that file we used to mention. And clock definition, these are inbuilt, like clock according to the clock spec file. So spec file is nothing but the clock speed, and according to speed, right, the time period is going to calculate, and the duty cycle, and timing exceptions, as I said, false path, asynchronous path, and all these things. Non-timing constraints, operating conditions like pvt conditions, while load model, and drvs max transitions, capacitance, fan out, and area constraints, multi voltage. If there are multi voltage domains, then we need to see that there should be any multi voltage domains, or power optimization techniques like upf file. This thing will be considered in upf file, so we no need to add it in sdc. So logical assignments, so if there is any logical light, so I mean the buffers for, or anything you can say it as. So in the .lib file is nothing but the library file. So in the library file, what we used to have, like timing and functionality, delay models, and like delay models are while load delay model, nldm, ccfs model. So these things, based on the input transients and the output capacitance load, these things are going to be calculated and put it in a library. So these things are going to do by the standard cell library, guys. So actually this is not responsible for the pnr team. And the pin and cell timing and design rules, and design rules are nothing but drvs, pvt conditions. So each library, if I take p28 library, 28 nanometer library, so in that library, for each pvt condition, uh, each and every pvt, if I am checking for 180 corners, there should be 180 pvt corners. And leakage, and for each and everything we need to have the leakage and dynamic power, and all these things we need to have. And in the left file is nothing but an abstract view of the cell. So abstract view is nothing but we don't consider let me show the abstract view if I had. No. So abstract view is nothing but we can it is only consists of only the metal one layers, that's what. And the physical libraries, and standard cell left, macro left, io left, and all these things. And left file consists of cell name, shape, size, orientation, and class. So orientation is nothing but R0, R180, R90, and pin port name, direction, layout, geometries, abstract, and blockages. Blockages are nothing but some metal blockages are there inside that. So these metal blockages are used for the interconnections between the uh, below that there will be poly active, so we need to connect those things, right? So for that this metal layer will be used. Antenna, so everything there is an antenna. So for every layer there should be an antenna. We need to consider that, since fabrication issue, so we will be getting the fabrication issues. And the technology file consists of the layers and via spec technology, like, so how much spacing, layer spacing, how much the vias should be spaced, and names and conventions and physical and electrical characteristics of vias, those things like direction, pitch, and width. Offset is nothing but if I one second. So offset is nothing but this is one of the metal layer, let us consider. So this is another metal layer. So this is the offset, from the middle to this middle of this metal layer. So let us consider these both are M1 metal layers. The distance between them is the offset, that is what. And if you can see this thing, right? So this is the offset. And resistance, capacitance, max, metal max density, antenna rules, and blockages, design rules are nothing but the fabrication rules. So how much will be the metal 1 to metal 1 spacing, metal, like which one will be the, like, if you consider, right? So M2, let us consider M1 will be horizontal, M2 will be vertical. So these things we need to consider. And M3 will be horizontal. So the alternative way, M3, M4, and M5, so like this it will be. Those things we need to remember. According to the technology it is going to change, we can't predict that. And technology file has to load before left file, since it holds layer information, so obviously. So technology file is very important. So without that we can't able to route the design, we can't able to place the standard cells, everything. So interconnect, like as I said, QRC tech file. So in this QRC tech file it will contains all the layer and capacitance of the interconnects, like which layer interconnect I need to place. So if you take, right, this buffer, from this buffer, so which layer, how much M1 or M2, which layer I need to use. So everything in that information you need to get that thing. And according to that, the lookup table, so lookup table is going to be calculated based on the length and how much the which metal layer, and based on these constants it is going to be calculate which capacitance layer, and length and capacitance based calculations is going to take place. And also used to generate extraction tools, and extract tools in the format of interconnect parasitics formats. So like it is in .ict for cadence format, like .itf in synopsis format, .ptf in mental graphics format. So these are going to be changed from every company to company. So that's what Then the two different naming conventions in technology: file left or interconnect parasitic. So this is map file is used to interconnect this both file, this technology file and the left file. So this is the interconnect file. So this will be going to map the file. So and the power spec file, there will be low power mode and different type of modes, like we can't say that which domain. So I can say let us consider this is my chip. So I can operate my chip at 1.1 voltage, or I can operate my chip at 0.8 voltage. So low power mode. So what it is doing was, there are different type of domains. Based on that we can operate. So if I need more power, if you are increasing the brightness of the screen, obviously it needs more power, right? That's what. So according to that, it is going to be vary. Tie up and tie low cells. So what are tie up and tie low cells? So this is the VDD. I consider this is the VDD pin. So I can't just directly connect these two standard cells directly. So with the help of some tie cells in between them, I can connect to that. I can't directly connect to that standard cell. So this there will be a huge power, and that is going to be damage my standard cells. So this thing we need to take care, right? Obviously everything we need to take care in PNR. So that is what. And coming to right next. And optimization drivers. Sometimes we don't need to use some specified nets. We no need to mention those nets in the cells, like I can say it as some buffers I don't need to use. If I having LVT buffers, I don't use in the data path. So that's those things I can use only size only. Or if I don't wanted to size some specified path, then I can mention it here. So if I don't wanted to size those specified paths, I can mention it here. Def file is an optional file. We don't say it as a required file, since according to this is a cadence format. We used to have list of location of all the components and vias, pins, nets and special nets, like everything, die dimensions, core dimensions. What is the difference between die and a core? So consider, one second, this is a die. Inside that there will be a core area, inside that there will be a rows. So inside that I can place a standard cells. That's right. Okay. And each and everything information, the spacing between them, and boxes, routing grids, power grids, pre-routes and def formats, and each and every information we used to have. And CTS spec file. So why we need to have this CTS spec file is uh, to run the CTS spec file. uh, what will be the insertion delay, skew target and max transient capacitance of what are the buffers need to be used, which buffers we need to use, which drive strength we need to use, and number of buffer levels, what is the tree depth, and list of buffers, and list of inverters. If there is used, we can use the inverters also, through pin, preserve pin, exclude pin, and each and every information we can have it here. And NDR file, and NDRs are nothing but double spacing, double width. We discuss it later. And macro models and each and everything. And IO file is an optional file. Pin and pad location, edge, order of IO placement. So which order we need to place, or which way we need to place, we need to have it in the in